everyone. All right, welcome to the final class of the quarter. Yay. So I'm a little sad because I'm not going to be the instructor of record next quarter for you, but I wanted to send a special thank you to the team that wishes to remain anonymous for the very sweet thank you note and gift card for my spilled hot chocolate from last week. So thank you for the very sweet gift. And just some logistic. So I will be involved with the class. I'm working with Bill to make sure that the transition is as seamless as possible. Barring my baby coming early, I should be able to still meet with you all up until the baby comes. And then I'm still organizing your senior design party that will be in June. I think we have a schedule for June 7th right now. So that's where we bring in industry. We do a really kind of big event for you guys to celebrate your graduation. So I'm still working on that. And we're going to be working with, so Dr. Tang says he's going to be meeting with each of the teams individually for 25 minutes at the beginning of the quarter so he can get ramped up. I'll be involved in that as well as the team leaders meeting at the beginning of the quarter to make sure that there is absolutely a smooth transition between myself and Professor Tang. And Vivek and Dr. Hu are also staying on board. So this is going to be as seamless as possible. I will still be in contact, so if you guys need anything, feel free to email me or come to my office. And so with that, we're going to get started with the senior design presentations, the last set of 8 for today.
Okay, hello everyone. Our team Greenlight is going to be sharing our new device imaging analyzer. My name is Alice. This is Mitchell. He's our leader. This is Stephanie and Teen.
So today I want to talk about the problem about cannabis impaired drivers. Cannabis is legalized in many states, and actually about 29 states. But the problem with it is, in specifically California, there's a 75 increase of marijuana-involved fatalities from 2015 to 2016. The main reason is primarily because of a chemical known as THC, which is a primary impairment contributor sort of causing these accidents. The main problem that I'm trying to address is basically US police officers do not have a standard tool like a breathalyzer to detect a quantity of THC concentration. They use things like sobriety tests or blood alcohol content in order to determine this, but this isn't sufficient. They turn to lab results, but the problem is they have to use blood and urine tests, and that can be invasive and time-consuming. Specifically here in Irvine, it could take up 1 to 2 months just for a lab result to get to a police officer. Our solution basically is a THC colorimetric assay that has been developed. We want to take this assay that shows a qualitative result. As you can see here, in terms of the blue, it shows a negative result, and then the gold is a positive result. We want to take this qualitative result, make it quantitative, because we want to show the police officers amount of THC concentration. Oh, sorry. So I want to talk about the competitors. So basically, it's a little bit hard to see, but the first competitor is the Draeger. They're able to determine the positive and negative result for a variety of drug tests, but it's not quantitative. The thing about the Hound marijuana breathalyzer is that it could produce results about THC about 0.5 nanograms per milliliter. The only problem is it's only meant for THC, so there's not looking such about an outlook beyond that. Now, the Liam's is the closest thing that compared to our product. They use saliva samples in order to determine like stuff using cortisol and testosterone to determine hormones. This is quantitative, but the collection process could take up to 30 minutes. What I want to try to do with our assay is trying to use one saliva sample to detect THC and then do it under 5 minutes, and then hopefully look to similar results using colorimetric gradient assays for other applications.
So in order to have a stable illumination and prevent exposure from ambient lighting, we started with a completely sealed box with only 4 extruded holes for 4 LEDs, which you can see on the CAD drawing. And it's on the cover, and the camera will be placed at the center. Like the 2D image on the right side, we simply insert our sample, saliva sample and use the microcontroller board to control the camera, use the LED to stabilize the lighting condition, and use the camera to capture the high resolution sample image for later analyzation.
So our major design criteria is to keep the data acquisition consistent, which means prevent leakage. There should be no other light beside the LED, and the light should be stable, which means it should be there should be avoid LED failure during the process. The camera should cope in to view the entire colorimetric assay and capture the sample without saturating the sample. And it's also the sample has to be perpendicular with the camera.
The image analysis was done using the MATLAB code, so we obtained a digital images of different THC concentration from Professor Kai lab. And the first step, we improve the quality of the image by removing all the noise and enhance the contrast. Then we apply the white balance and color correction to normalize all the illumination condition of all images. Then a region of 50 by 50 pixels will crop out of the image from the center of the droplet. And then the crop image were converted from the RGB to the LAP color model. And the average value of LAP were calculated and used to build the calibration curve. And then we figure out that the correlation between the B value and the THC concentration. This is reasonable because like when the THC concentration change from the 0 to 500, the color is changed from the blue color to the yellow color. And in the next stage, we will observe more, we'll obtain more THC concentration and build more accurate calibration curve.
So we have three primary concerns. The first thing with the LEDs not working is caused underexposed images. So with that, we have the light calibration and we have the alternate curve for a low light condition. The second one is our focus that cause the blur images. So we have the camera and the images with the fixed positions. The last one with the camera, which it cannot capture the images. Then we have, if the processor cannot get the signal from camera, then our device will have warning message. Please check the connection between the camera and the main board or press the reset button on the device. Next, please. So here's the list of the component and the costs of our prototype. Camera, 3D printing, and the Arduino is cost $40 for each. The LED and the electrical component will add up to $134. And we're using the available on-campus resources, so we still stay within the budget.
So in terms of the market, in terms of the drug and alcohol test manufacturing, is about a $2.3 billion and growing industry until 2022. We primarily want to target employed officers, and then here in California, there's about 70,000. In terms of sort of the demand for this and trying to get them interested in using this sort of a device, we want to compare it to something like Colorado, which 33.2% use cannabis daily, and out of that 32%, 18 use cannabis before they drive. So there's definitely a reason why they want to be able to make sure if someone's impaired that they're not under THC, and we want to make sure to manufacture this about $200. So in terms of our business plan, I want to make sure to get this to third-party distributors that we're able to distribute this to police departments and forensics labs that could get this quickly and efficiently to police officers. So that way it ensures that we stay relevant within the market and not too long before the market goes stale.
So I'll go for spring quarter. To complete the prototype by April, find the third-party manufacturer by May, and address Europe and future direction by June. Those are our three major milestones. Thank you for your time, and we're up to any question.
I would really want to talk about something like that, but in terms of like the digital images that we have been using currently, it's really hard for us to determine what's a false negative and what's a false positive because we don't have the real samples to actually test. We've been just given digital samples and we're just basing that on the color change from blue to yellow. But hopefully when we want to test for something like THC, that there's not some sort of like negative like poppy seeds or something like, you know, if you eat some sort of food and that sort of conflicts the results. That's what we want to test when we want to sort of optimize our design in May.
What is your desired limit of detection?
So the desired limit of detection, if you could go back to the Hound breathalyzer, they talk about the 0.05 nanograms per milliliter. And this is something that they're trying to do in Colorado for limits of detection. And also in terms of like sort of the industry aspect, because hemp products, they also use this sort of standard. They use 0.05 nanograms per milliliter to detect, to make sure that their product is up to standard.
So why is this better than the breathalyzer for marijuana?
So the reason why this would be better than the marijuana breathalyzer is because our outlook for possible applications for similar colorimetric assays with this gradient, if we could apply that with saliva and then do the same, if there's a problem and a need for that, we could develop for that, hopefully, in the future. Yep.
Hi, I was wondering what image processing software you were using.
Yeah. Oh, we've been using MATLAB.
Oh, okay. Thank you.
Yeah. Any more questions?
Is it battery powered, and how long do you think the battery life is right now?
So right now, in terms of our prototype, we just sort of been hooking up with the computer and then making sure that it goes from the Arduino code is sort of controlling the microcontroller. And then hopefully we get those images from the Arduino and then put it into MATLAB. And then maybe along the roads that we could sort of develop this sort of continuous process where it takes the image and then it's sent to the computer for analysis. Yeah. Any more questions? Currently, we're not testing this with people who have been using THC, and that's just mainly because we want to make sure that we actually have some sort of proof of concept with the real world application. Yeah, but thank you. Yep. Is there any more questions? Yep, thank you.
I meant like. You want to have with great pride comes great responsibility.
Hello, we are Numalife, and we are developing a wearable sensor to detect sleep apnea in premature babies. My name is Kyle Hansen.
Oh, I'm Melissa Lopez.
My name is Mohammed Abdurrahman.
I'm Jasmine. I'm me.
All right, so sleep apnea is the most common medical condition in the 15 million premature babies that are born each year. It is defined as 20 seconds of absent breathing. Of the premature babies that suffer from sleep apnea, 40% suffer from central apnea, which is what our device will target. The problem with current monitors is that they're bulky, have wires, and have many false alarms. As you can see in the image, there's a strap that goes around the chest of the baby, and there's a wire that leads from the strap to the monitor. Whenever the baby moves, the leads on the chest can pop off and cause a false alarm. In 1999, 44% of premature babies were sent home with a monitor. However, in 2015, only 8% of babies are sent home with monitors. This is primarily due to the high frequency of false alarms. Physicians don't want to prescribe these devices, and parents don't want to use them. However, there's still a need for these devices as $80 million is spent in commercial products.
This is where Numalife comes in. So our goal is to develop a device that is both compact yet highly sensitive and is also wireless. Some features that we want to include on our device are an SpO2 monitor, accelerometer, a higher accuracy, meaning less false alarms, and also the biggest thing that sets us apart from current devices is our patent-pending vibration stimulation therapy, which our device will vibrate in response to a detected apnea episode, and that will encourage the baby to start breathing. These are some design and acceptance criteria that we would want for our device to meet. First of all, it needs to be compact and comfortable. It needs to have a compatible adhesive so that it's not irritable on the baby's skin. It needs to last a long enough period of time for the premature phase of a baby's life. It needs to be wireless, and the data acquisition and analysis needs to be accurate enough, and we're aiming for a 90% success rate. This is our current prototype. We have our sensor attached to an adhesive patch that goes through a voltage divider that's reading into the Arduino and our LabVIEW interface. In the first image, we've attached the adhesive patch onto a balloon, and that imitates the premature baby's size and breathing rate. We've also tested it on ourselves, and that's an image of me with the device on my chest. And we've also tested it in other places like our abdomen. And so we had some preliminary breathing data comparing the difference between chest and abdomen breathing.
So as of thus far, the cost has been $91.43. That's split up among 3 major departments: the electrical, sensor, and chemicals used to make the sensors. What makes us different from our competitors is that our device is simple. In other words, it's user-friendly. It's one component, so it's easy to store, easy to place on your body, and it is significantly less costly than our competitor devices.
So we have a few validation testing to ensure that our device is up to par. One is durability, which would ensure that the lifetime of our device meets the acceptable criteria. And then there's sensitivity to ensure that the device is picking up on the baby's breathing rate. We're also removing hysteresis by plotting the cycle graphs on top of each other to get an average. And there's a response time test to ensure that our device has a response time under 0.7 seconds. We also have a few potential failure modes that we have listed above. One of the major potential modes is when the sensor breaks or when there's no detection. And to counteract this, we have replacements available. There's also signal loss, which we're aiming to address by embedding an alarm into the device itself. And finally, a graphical analysis, which the parents may not be able to understand. And we're providing a telemedical support system to address this problem.
So of those premature babies that suffer from apnea of prematurity, we plan to target and market to the 40% that suffer from central apnea of prematurity. We also plan to take a percentage of the $19.6 billion that is spent on premature medical and healthcare costs in the United States annually. So we plan to sell our device system to hospitals. The device system is composed of a standalone monitor as well as replaceable sensors and adhesives. From there, the hospital will rent out the system to patients, and we will then take a percentage of the rental cost. The patient will keep the monitor at home until it is needed. They will then return it to the hospital. Then a product check will be conducted, and replacement supplies will be purchased by the hospital. So our spring quarter goals are to test and receive feedback on our prototype 1.0. We'll also be developing an app and a machine learning algorithm. From there, we will be using feedback and testing to create our prototype 2 in May. And then any testing or fabrication issues that we have will help us create our final product in June. So thank you for listening. If you have any questions, please feel free to ask.
Detection of apnea, so we want to increase that to 90%. Yeah, detection of an apnea episode. Yeah. So the sensor is a strain sensor, and we're placing it on the chest. So when the chest volume changes, it's detecting that change in volume, and we're correlating that change in volume to breathing.
Why did you choose an adhesive design?
So we considered a couple of different options, a band or on clothing, but we felt like an adhesive was the best, would provide more accuracy, and which is the major component that we want to improve in the current products right now. Yeah, actually, there is a Harvard study that used vibrational mattress pads under the babies, and they've shown that it does interrupt an apnea episode and helps them to start breathing again. Yeah.
Do you plan to wirelessly connect it to a phone or your own hardware device?
So that was part of our features. I kind of glossed over it, but we'll have both an app device, an app on the phone. But we sent out some surveys to parents, and they wanted both the phone app and a standalone device in case their phone fails. So we're going to have a standalone alarm device.
How long do they wear the patch before they replace them?
We haven't determined that yet. Yeah, we'll need to do further testing.
Do you know if there's a reimbursement for the bands that they get sent home with from the hospital with these new patients?
Like an insurance. I'm not sure about that. I just know that the parents can rent these devices.
You mentioned 100,000 cycles for durability. So, and then you also mentioned that you expect these devices, your business model is for the hospitals to rent these out. So what is the lifetime for one of these devices?
Yeah, that. We haven't determined the exact lifetime, and we still need to do durability tests on the sensors itself.
How did you come up with 100,000 cycles?
That's a number that I wanted to test it at, but I haven't tested at that number yet. Okay, thank you. Do I give this?
How does this work? Okay. All right, good evening, everybody. So we're Team Aflux, and we're an Edwards Life Science sponsored team, and we're using their intellectual property with our project. My name is Jason Brown, and
I'm Derek.
So the disease state that we're dealing with is atrial fibrillation. And the major problem with AFib is that it's an arrhythmia of the heart. And with arrhythmias comes stagnant pockets of flow, of blood flow. And that those stagnant pockets lead to clot formation. And the problems with clots forming is that they can come out of the heart into the bloodstream and cause ischemic strokes. So the prevalence of non-valvular atrial fibrillation, which is the exact disease state that we're dealing with, there's 7.5 million cases that are expected in 2018 alone. And as I mentioned before, the real risk that we're dealing with is stroke, and it increases the patient's risk of stroke by 5 times. And studies have shown that 90% or more, the clots are forming inside of what's called the left atrial appendage. It's this appendage that comes off the heart where there's not very good flow there. So that's the anatomy that we're dealing with, is with the left atrial appendage.
So here are current competitors that are currently out on the market right now. The first on your left is Watchman, which is an occlusion device for the left atrial appendage that was developed by Boston Scientific. One of the biggest disadvantages for this product is that by occluding the appendage, you're actually decreasing the efficiency of the heart, as the left atrial appendage can no longer function normally. Another really big disadvantage for this product is that patients must also be able to be on warfarin to be eligible. The second on your right is what is currently the gold standard for treating patients suffering from atrial fibrillation, which is warfarin. However, one of the biggest disadvantages for this is that by being on a blood thinner, patients now must live a very inactive lifestyle, as a simple nick could cause a result of a major blood loss. So here's our proposed solution. By increasing flow into the left atrial appendage, we're preventing that stagnant flow that Jason was talking about earlier, while utilizing the normal functions of the heart so that we can increase and maintain heart efficiency. So what we developed is this elbow design, where the inflow is actually anchored in at your left upper pulmonary vein, and your outflow is anchored in at your left atrial appendage ostium. On the bottom left picture is actually one of the first proof of concepts that we decided to do, which is just a 3D printed stent so that we could kind of get this concept idea into hand. In the middle is your 2D DSX CAD sketch file, which then in turns, when we give it to our lab, they then cut a hypotube on your right of most farther image where it can then be shape set it into the angle that we want for anchoring.
So as far as design requirements go, when we were putting this together earlier in the quarter, we were thinking of it as the entire system as a whole. So that's delivery system, how you get the implant, plus the implant itself. And we came up with a document that was 8+ pages long, and we had to redefine the scope of our project in order for us to have some success in this quarter. So we decided to mainly focus on the implant itself, and really the design. So when we're thinking about the design of an implant, one of the major concerns, especially with something that's deployed in the heart, is that it needs to stay still. It needs to stay in there. So we have this kind of poor man's DFMEA of requirements for this device. So number one, it needs to stay in position and not clock, because if it clocks, it's no longer pointing into the left atrial appendage, and that flow isn't being increased anymore. To go along with that is the dislodgement of this implant. It can become dislodged, so part of the design requirements for that is just how the stent is able to be deployed, the radial force of that stent, and how the stent interacts with the surrounding tissue in the vein. And one of the last things we came up with was turbulent flow. And so this turbulent flow can actually lead to hemolysis of the blood cells, which in turn would produce clotting, which is what we're trying to treat here. So that would go against what we're trying to do.
So here's the current market that we want to target, where the areas marked in red are the heavily high hospitalization rates for patients who suffer from atrial fibrillation. And every year, about 4 million people are actually hospitalized because of this disease.
Business model. So I think the main idea I want to get from this is that there is a CMS reimbursement code that already exists for the Watchman device that Derek was talking about. So there's a pathway to get insurance reimbursement right away. And from there, the patient population that we're trying to treat is approximately 50%. 50% of patients either can't be on warfarin or they choose not to be on warfarin, and that's kind of the main advantages of us is for patients that don't want to be or can't be on this blood thinning agent. So as far as spring goals goes, we really have to focus on our design of our implant. So that just means a lot of bench testing. That bench testing, so the dislodgement forces and torque forces within the pulmonary vein with either cadaver hearts or porcine hearts, and then reiterating our design and really dialing in, finalizing the design. And along with that is a shape set fixture that we can get that nice angle that what we're looking for with our device. And finally, towards the end, we want to start thinking about delivery systems. So how are we implanting this device, this implant? So that's our high-level goals for spring. Yeah, I think that's all we got. Are there any questions? Correct, yeah, so that's a very good question, and that's where some of the bench testing comes from. At Edwards, there's a FlowViz system where you can actually track the flow of fluid, right? And so that's where a lot of the bench testing will have to come from, is testing that flow and seeing what sort of turbulent forces. Yeah, that's a great question. So, if we look at our super early prototype where we're like, we just had 3 basic designs and we printed them off just to have them in hand. If you see that angle is very, very sharp, right? I can imagine if there's flow going through that, you're gonna get all kinds of turbulence. Now the image on the right has kind of this more smooth flow. So that's kind of why we think that if we shape set this stent into a more gradual curve, that will be in our favor. We haven't.
So you said that you wanted to attack the markets that don't take warfarin, right? So if you implant this stent device, won't they have to take blood thinners anyways?
No, because one of our designs that we are going to incorporate into the stent will not have them be able to.
So part of the design of the actual stent is that you won't have to be on blood thinners.
Oh, it's a drug-eluting or?
No, so one of the major advantages for some of the stent technology that Edwards already has in some of their IP is that they're very, very low stroke rate. So that's some of the learnings that Edwards has learned in the past that we can implement in our.
Thank you.
Does it self-anchor just because of the fluid flow through it, or how does it anchor?
Yeah, so if you design it to be slightly bigger than the left pulmonary vein, there will be that radial force, right? And then if you look at the edge of the stent there, if there's any movement of that stent, some of those edges that's popping out will actually grab onto the tissue. And so that helps with some of that anchoring initially. And furthermore, you can implement some characteristics of the stent where you get tissue ingrowth. And so that will help ultimately anchor it in for the long run.
Why are there more cases east of the Mississippi as opposed to west of the Mississippi?
I didn't hear it.
So go back to your map of the U.S. Why is there more red east of the Mississippi as opposed to west of the Mississippi? There are more cases over there.
Waffle House. Have you ever seen that map?
Really?
I mean, I guess, yeah, I guess they eat a little bit differently over on the East Coast. That's my only explanation.
Right. One last question. You mentioned your reimbursement strategy, but what about your FDA strategy? How are you going to get this thing approved?
That's a great question. So that's a long list of tests that we could probably take all night. Design validation, DV testing, lots of thrombogenicity, biocompatibility. There's a ton I'm forgetting, but it's a long pathway for an implantable device.
Who's up next?
PCR bot?
So hi everyone, we are group 24 PCR bot. So this is our team. I'm Roxanne. This is Shen Jie. This is Jia Yi Zhao. This is Dan Feng Jiang, and this is Simon. Now let's give the microphone to the JS.
So the problem here is it's very hard to use the current PCR method to detect sepsis disease. And why this is important? Because sepsis is actually affecting 30 million people here, and it killed 258,000 people in the United States every year. The sepsis disease has very low concentration in your blood. So when the patient goes to a hospital, it usually takes several days to detect what kind of disease they have, and then doctor can give them appropriate initial treatment for antibiotic. And sepsis has, the survival rate for the sepsis is decreased by 10% for each hour of delay. So the specific problem is the current PCR can only handle very small volume samples. So it leads to very small sensitivity, and it is very hard to detect. So our team is trying to solve this by using large volume PCR method. And Jiayi will talk about the prototype.
And our method is applying an automatic large volume thermocycler use the water-based method. And the basic principle of this is transferring samples between the two water baths to reach the thermal equilibrium to complete a PCR reaction. And our idea is inspired from a paper named A Rapid and Low-Cost Thermocycler for Low Resources Setting by Grace Wang's group. And as you can see in the picture, their model is built on the condition in extremely low resources. And our design developed it by reducing unnecessary motion. And the logo model can demonstrate our mechanism. The mechanical arm is rotated by the motor, and the gravity enables keeping the basket of sample tubes vertically. And I'll hand to the
Thank you. So let's talk about the design criteria. So first we need two independent water baths, and the temperatures of the two water baths will be 55 and 95 degrees Celsius respectively. And the number of the sample cuvette will be at least 4 for one operation, and the number of the thermal cycle will be at least 45. And the time between the water bath transition need to be less than 10 seconds. And the water bath temperature variation will be less than 5 degrees Celsius. And the water bath dwell time need to be user adjustable and independent for each water bath, varies from 10 to 30 seconds. Now, Shunwen.
Okay, I'm going to introduce the advantages of our design. So the picture on the left shows the methods that currently be used in lab for PCR thermocycling. A thermocycler device will heat and cool the samples for many times. However, there are some problems with this method. For example, only 200 microliter cuvettes can be put into this device. So it requires people to pipette a large sample into small cuvettes. And the shear force created by pipetting may destroy some of the sample droplets. And the sample volume in small cuvettes is too small to be sensitive for detection. To solve these problems, we built a mechanical arm which is controlled by a step motor to directly move a large container with samples between a hot water bath and a cold water bath. In this case, there's no need to separate a large sample, so it will reduce damage to the sample droplets. And a larger sample volume is also good for detection, which makes the detection more sensitive and accurate. Next. So a thermocycler device in market usually costs around $3,000. However, by looking at the budget form of our design, the total cost is around $120, which is much cheaper than that. And next is Rosie.
Thank you, Simon. So there are several potential failures on our prototype. The two major parts are from mechanical arm and the sample holder. So for the mechanical arm, because we use several step motors originally to control the movement. However, it's too many step motors, which makes the movement too hard to control. And another another problem of the mechanical arm is the number of runs it can run at each time, because too many step motors are involved. Like the first problem, the movement is a problem. Another one is it's really hard to control. We cannot get into the desired position, or it will break easily after several runs. So instead of using several step motors, we decide to only use one or two. It's really easy to control the motion. And the second one is we worry about the sample holder will spill out of the container. So because the large movement will cause the sample waste, so we add a lid to prevent the spill of the water, and also move a little bit each time. For the marketing, so our major marketing is for the hospital and the labs, and because there is an increasing trend of the success prototype marketing, which is in 2014 we have 57.3 billion, expect to increase to 81.1 billion in 2020. And also the target market is from the US and from the China, have like different billions. There is a huge market. For the business model, our prototype are famous for the efficiency and the sensitivity. So this is the step we plan to do. Now let's head to JS.
So in spring quarter, we are first gonna finish making the prototype, and then we are going to test it and make sure it can meet all our requirements and criteria. And finally, we will make some improvements on that in order to make it more stable and better performance. And thank you. And any questions?
Micro, and for the previous version that they already have right now is 100 micron.
So it's 20 times larger.
And why do you only use 4?
I mean, at least 4. Yeah.
Okay. So you can scale this up.
Yes.
Where are you in terms of prototype development?
Wait, what?
So
the status of the prototype.
right now we are on the stage of building the prototype. We are using the logout model to make the similar movement on the left and right water bath.
Do you know what type of qualitative procedure you're going to test for, like when you transition from the 55 to the 95-degree Celsius water bath? Like, how do you know there's not going to be temperature change between the water baths? I know it's like less than 10 seconds, but I'm worried about like there might be certain degree changes that might affect this.
Yeah, that's a really good question we think about, because when a sample holder will submerge into the water bath, there's a little bit temperature change. But we plan to use a very large water bath, which have a lot of liquid content on it. Only small volume of sample will not affect like large volume of water bath. So it's 12 diameter and 3 inches height.
12-inch
Yeah.
diameter.
Oh, sorry.
And 3
Yeah.
inch height.
Yeah.
And that's adjustable. I mean, we don't have to use that. We can change once our prototype is building up.
Yes.
Do you foresee this as being an enclosed system or like open air?
Oh.
Down the line.
Do you mean the water bath?
Yeah, like is it all going to be contained in some big box, or is it just going to be like open?
So it will be opened. So the water bath is open, but the cuvette is closed. So they will be submerged into the water. Any more questions?
Thank you.
So hi everyone, I'm Brandon, joined by Sean, Haneen, and Joseph, and we are MedLight Surgical.
So at MedLight Surgical, we're working on making a surgical headlamp, which is an illumination tool used by surgeons during surgery. So the main components for a headlamp includes a lighting source. So right now, the most common is the LED. There's a power source, heat sink, fan, and then this is all thrown onto a headband. So in 2009, there are about 48 million surgeries in the US, and from the table you see on there, you can see the total percent of those surgeries that use a headlamp. So the big ones are the cardiovascular and the thoracic that use the headlamps, and these are really mentionable because they are long surgeries.
So some current issues with LED surgical headlamps right now is battery life, lighting quality, comfort, and safety. And what we're mainly trying to address in our model is the battery life, the lighting quality, and some safety aspects. So we want to have a battery that lasts 4 hours or more, have consistent lighting quality and color, and also have good safety features regarding the brightness levels of our product.
So our prototype uses an existing model with features reverse engineered for an improved and cost-effective design. We use current battery technology to provide more than 4 hours of use in the operating room. Our LED is selected based on a criteria of 1,000 lumen output, a color rendering index of 90 or above, and a color temperature of 5,000 Kelvin. Our LED cooling system will be designed to maintain the LED temperature at 40 degrees Celsius or below, and our automated dimming feature will provide a novel and innovative product for inexperienced surgeons.
Okay. So we purchased a cheap headlamp, and we're gonna have put the battery pack in the right side, and then the Arduino plus the accelerometer on the left side, and we're gonna put the LED plus the heatsink and the fan in the L-shaped luminaire in the front, and we're gonna run the wires from the batteries to the Arduino and to the LED in a clockwise fashion, and we're gonna develop a luminaire system to replace the existing luminaire.
So our more novel approach to LED surgical headlamps is using an Arduino and accelerometer to have an automated dimming feature. So as you see in the two pictures there, as the surgeon has their head at an angle on the surgical site, the light will be fully illuminated. And as they have their head go up to a more horizontal orientation, the voltage will drop and therefore dim the headlight. This will prevent a bright light from shining onto any other people in this surgical room, and also provide for a hands-free experience during an operation.
So for the batteries, we decided to go with what the Tesla cars use, the battery cells. So that would be the Panasonic 18650 batteries. So already compared to what's out there on the market, it's either better or equal amp hour capacity. But then we talked to an industry professional who focuses in battery design, and he introduced us into the Samsung 21700 battery, which is a little bit bigger in physical size, but has a much greater amp hour capacity. And so for the wiring of this, we'll have about 3 or 4 of those battery cells in series, and then those will connect to the Arduino, and the Arduino will fluctuate the voltage and current based on where the head is, and then that will feed into the LED and the fan.
So in order for us to achieve this, the lux output, the required lux output, we need to have a properly designed lensing system. Most surgical headlights uses a 3-lensing system. However, we found that the 3-lensing system does not provide a fully uniform light beam. Based on our optic simulations, we found that a 4-lensing system provides a more uniform light beam compared to the 3-lensing system. Go ahead, Brent.
For the potential failures for our design, the 3 big ones are the accelerometer, our Arduino. It could potentially take more power than save. So we're creating an on-off switch for that. And then also
in case there are any glitches, so we'll be updating and troubleshooting this code and make sure it's working properly. Also, the battery pack, due to it being lithium ion, it has a higher potential of catching fire. So, like I said, we talked to an industry professional who focuses in battery design, and we've talked about different safety features to add to the battery pack.
So once we go to market with our product, our three main competitors are CUDA, Ronin, and Onova. Unfortunately, that it's out of aligned. Since surgical headlights does not have an industry standard, our competitors claim that their product is extremely bright, sometimes too bright for most consumers, right? And their battery life does not meet the 4-hour average for surgeries. Our product will have a lux value of 70,000, a battery life of 4 hours, a spot size of 130 millimeters, at a competitive price of $4,000. So since we're using an existing model to show our proof of concept, our prototype cost is relatively cheap. So this cost does not include the manufacturing and materials needed to design our headset, which would drive up the cost to $1,000.
So we want to market our current LED headset to all surgeons in general. However, inexperienced surgeons will make more use of the dimming feature because they tend to move their heads around a lot more during an operation. There's an approximate $50 million US market size for this product, and we will be manufacturing and have surgical equipment distributors sell it to hospitals, academia, and surgical centers. Through online marketing, we'll have a list price around $4,000, which will be competitive to other products on the market. So overall, general next steps is to continue to code and troubleshoot, create our L-shaped luminaire and throw it onto the existing headset that we purchased. And if we have time, we'll incorporate 2 battery packs and determine the need for a fan. And thank you, that is all. Are there any questions? Yeah, definitely adding, batteries, if we want batteries on the headset itself, which our industry mentor was definitely kind of looking into, those will add more weight versus the luminaire shouldn't add too much weight. It's mostly on the batteries and the possibly the Arduino on the headset.
The lensing system is relatively light because the lenses are at least 20 millimeters in diameter, so they're relatively small.
So how heavy, what's your design criteria? How light does this need to be?
Right, so
Under 15 ounces, so less than a pound.
And what are the current ones on the market weighing?
so they're around like between like 12, 16 ounces. They differ widely.
The lightest one would be like 7 ounces.
So you're not going to win in terms of lightness, but
Probably not. We'll see.
Weight obviously is an issue, as well as power. It leads me to wonder, how did you choose an Uno as your microcontroller? Because that's relatively larger compared to most Arduinos Balloon have and things out there. They can also do LED.
So definitely for our first prototype, we'll be making use of the Arduino Uno and making sure we're not very well versed in coding, so we're definitely doing that right now. But as we move on to the next phase of the prototype, we'll definitely look into smaller micro controllers. Any other questions? All right, thank you.
Hello, we're Promotion, and we're making a cessation device called HuffBlock. Here's our lovely team, starting with our team lead, Navo. Then we have Priscilla, Clinton, Julie, and myself, Mary. So what's the problem we're trying to tackle? It's smoking. It's the leading cause of preventable death in the US, causing diseases like COPD, chronic bronchitis, and lung cancer. Almost 1 billion people in the world smoke every year. 6 million of those people die every year. 68% of those people try to quit or want to quit, and 55% try. Only 6% succeed, so there's always a lot of people, throwing their life away.
So our group has designed a wearable to provide mental awareness in smokers to slowly help them quit. The picture on the right is our current prototype. It's a IMU equipped on a wristband. First, IMU will check for the movement going towards your face, then it will check for the orientation to see if the gyroscope value is within the range. In the code, we define this code and calibrate them for each user based on the position how they actually smoke. Once we have the code, we'll check for how long is the rotation. This is how we distinguish smoking with eating or drinking, since eating and drinking always have smaller movements and more frequent. Finally, positive reinforcement will be gained for behavioral change. These are our CAD diagrams. Basically, it's a watch-like design. This part is the bracelet, and the part in the middle is the display.
Thank you. So here are the building blocks for our design. We understand that because smoking is such a frequent motion, we don't actually need 100% accuracy. We'll live with 90%. We thought it was really important that if it's wearable, so that our user could wear it around the clock, and so we want to make it waterproof so that you don't have to go through the hassle of taking it off when you're showering or doing the dishes. And ultimately, we want a product that can notify our user of progress and ultimately utilize positive reinforcement to actually have that change in behavior. So some modes of failure. The biggest one right now is a user. We are working on a design that will make it obvious and uncomfortable when it's not sitting on your wrist the way the code expects it to. Some other ways that it fails is if you're smoking in a really unusual position, such as if you're laying down, or if you try to trick the device by moving your hand really slowly. But we're working in spring to expand our library to account for these things. And now I'm gonna give it to Priscilla, not Julie, for some market numbers.
Thank you, Clinton. So our current manufacturing costs are $22.10 for 3 single unit builds, which is kind of odd. So if you divide that by 3, it's $7.50 for 1 single unit. Next slide, please. So in the future, we hope to produce our product in bulk, and that should lower the cost by at least half, which would bring the cost down to $2.73 from $7.50. Next slide, please. So why should you choose HuffBlock as your smoking cessation method? Well, first of all, we don't use any sort of chemicals to encourage our user to quit smoking. Instead, we provide positive reinforcement along with notifications daily through text message, including notifications telling you how much you've saved from not smoking like in the past week. And as far as cost goes, our product fits between the amount that other cessation devices are, which is like $40 to $80. But our product is actually only a one-time purchase, unlike other smoking cessation devices where you have to purchase like e-liquid or like more nicotine patches. And here's Julie, and she's gonna talk about the market.
Every year, people pay a big amount of money on smoking cessation products. As you can see here, in 2015, the global smoking cessation product market is valued at $11 billion and is expected annual growth rate of 17% in the next 10 years. For our potential customers, it generally falls into 3 categories. First is people who tried other methods but failed, and those with low socioeconomic status, and military service members.
Okay, so our business model, since ours is a tangible product that's going to go to the market, we're going to go to a business, B2C, a business to consumer. We're also looking at the B2B business, but we're going to go forward with the business to consumer model. Our channels, primarily, we're going to go online. First, in the beginning, start a Kickstarter campaign to gain capital and traction, and then move on to Amazon, which is a big behemoth in the online interface. Sell it on Amazon. We'll also sell it on our own company website from our own products. Secondly, in store, like other wearables in the market, people are selling it in Best Buy and in Target on the shelves. So our device will also be on the shelves. So our spring quarter goals are in the next 3 months. The first month of April, we're going to be preparing and practicing for our various Mrs. competitions. This is also we're going to celebrate some birthdays too. In May, we're going to finalize our MVP, our minimum viable product. For this, our goal is to get our libraries going, our coding library even more precise. Test for accuracy also. We want to make sure that we don't want to mess up any readings between eating with smoking. And finally, build a nice wearable product that's easy to show people. And in all 3 months, I put it in June, we put it in June, but in all 3 months, we want to keep doing more customer discovery. We want to see how customers are actually reacting to the product, see what we're missing, what they actually really want from us, and make sure that our product is a viable thing for the market. Thank you. So any questions? So we have a very bare minimum working, that can actually read the signals, but in terms of stylized, it's not very pretty. Right now we have the Arduino, put it in with the accelerometers, gyroscopes, but with the rubber band that holds it together. Yeah, and soldering, but it can pick up the range of motions. Not precise as we want it to, but we could definitely read it.
And so does it tell your phone how many times you're actually smoking? Is that one of the things it's going to report, or is it just going to say, you did better today than yesterday?
Right, so we haven't worked on the app side right now. It just counts how many times it has the motion. And if it's less than your last session, it'll play a Mario song. Yeah, one ideal was to kind of work on that positive reinforcement. We want the user to be able to customize and play, like their favorite song or a song that really gets them going. But that's really down the line.
So does it notify you as you're doing it, like the beep, like hey?
Right, so we haven't worked on it either, but we want to be able to essentially determine when they ash their cigarette and kind of notify them the duration they smoke and how many drags compared to last time. Right, so the acceptance criterion for the IMU, so the gyroscope, it has a really specific yaw, pitch, and roll. Right now, it's just determined manually, but ultimately we want it to be able to be calibrated. So what the user would do would to hold their hand to their face, like they actually have a cigarette, and just set that value. And those angles is specific to that orientation. So if it was out here anywhere, it wouldn't satisfy it. And it has to hold angles here, and we have an average drag time of 2.5 seconds, and there's a lower limit and upper limit. So if you're scratching your face, it's not going to detect, and if you're scratching your face, well, no. Essentially, it checks the values of the gyroscope. So if your hand is even moving near your face, then it won't count.
One such avenue we were looking at is the motion data sales. We can give it to researchers about when we track the motion of a hand to mouth. We can give it to different communities, academics to help them with their research. Yeah, that's pretty much what we're looking at right now. We're thinking about like a business-to-business model, which I need to look into more, research more of how our product can do that. I know a lot of like Fitbit, Apple Watches, and Samsungs, they go through that model, but we want to know how we can do it too.
So with the existing smartwatch market kind of on the rise, have you guys thought about maybe utilizing that market, the accelerometers and stuff that already exist in the smartwatch market, maybe coming out with like an app or something?
Yeah, originally when I talked to different people about this idea, one professor said, why don't you just do an app for this, because the components that we have is the bare minimum that smartwatches have, all smartwatches have. We thought about it, but it's a great avenue. We're definitely looking at it. We're not saying we're not going to do it, but we also wanted our own product because it's definitely cheaper to buy ours than an actual smartwatch, because ours is for an addiction-centric type of product.
Hello, everyone. I'm Nini. This is Evelyn, Truck, Zhen, Lucy, and Alex.
Yes, and together we are Spiral. As a team, we are trying to increase patient adherence to respiratory therapy. Currently, the problem with traditional incentive spirometry is that it's very bulky, it's not very motivating, it's frustrating, and it's painful. 86% of respiratory therapists in a national survey agreed that this patient adherence was a problem and needed to be improved. And the top 3 reasons for this being an issue is that the patient wouldn't do it at all, they would forget it. It wasn't used effectively or as efficiently as it should, or as often enough to actually show any results. And part of the reason here is also because in order for the patient to actually be monitored, that they're actually going through this therapy, the respiratory therapist or other healthcare provider has to physically be in the room to watch them do it. So as a team, we are issuing a 2-component solution to this problem. The first part is to use wearable stretch sensors to take away the bulk and have a patient monitoring, as well as a motivation component with a game-based therapy to actually lead these patients through the breathing exercises. And Nini will explain exactly how we're going about that.
All right, thank you, Evelyn. So as she said, the first component of our device is the sensor. So the sensor is connected to an elastic band that the patient will wear around their rib cage. And as they inhale, the sensor will stretch, and as they exhale, it will relax. And so this translates into a resistance change in the sensor that then is read by the Arduino and will be sent to the software, which is our second component. And so since every patient's waist is a different size, and because resistance is a very important thing for our device, the first thing that the game will do is it will calibrate it to the resistance that the patient has during the reading. So the patient will be asked to inhale and exhale, and this will create a threshold value. And so as they inhale, it crosses the threshold, and it will move the plane to the right, and as they exhale, it will move the plane to the left in our game.
Okay, so currently our sensor is connected to a game that's similar to Space Invaders. As you can see here, she's inhaling, so the character is moving to the right, and the character moves to the left as she exhales.
So there are many features that we want to focus on for our device, but for this prototype, mainly we want to prove 3 main concepts, and that is to make this device reusable in terms of making it last about 1.5 hours. This number is based on the fact that the sensor has a certain amount of cycles before it fails, and we want it to at least reach 1.5 hours. And the second component is to make it comfortable in terms of lightweight and making it non-obstructive. These numbers are kind of based on the weight and size of a belt, for example.
Respiratory devices in the market have several drawbacks. For example, the traditional spirometer is good at measuring precise non-capacitive, but it is obstructive and expensive. Incentive spirometer is much cheaper, but it can be only used for guiding patients to train their lungs. Airway clearance vest is a handoff device. It can dislodge mucus in patient's airway by shaking, but it is expensive and not portable. Our product combines their advantages. It is portable and affordable. It costs $70, and the game can motivate patients to train their lungs. And not only is it hand-free, it is not obstructive.
So as Jen mentioned, our device costs $70. To make our device, it costs around $58. We want to do a 20% markup, which brings the market cost to around $70. We want to note that this is the cost for our current prototype, which uses Arduino and a band. And as you can see from the pie chart, that makes up the majority of the cost. For our final device design, we want our device to be wireless using Bluetooth, and instead of a band, we want to use an adhesive. This will bring down the cost to make our device, which will bring down the market price. A potential failure is sensor wear. The sensor has been shown to reach 1,000 cycles without discernible degradation. Furthermore, normal breathing has low strain, and we believe that at a lower strain, the sensor can be used for a longer period of time, and we will test this next quarter.
Okay, so another problem with sensors is possible hysteresis. Again, this could be corrected through software after we're able to characterize this problem. And as for noise and artifact, we could use the software or hardware filter, or we could use multiple sensors as they act like differential measurements.
And as you can see, there's a relatively large market for respiratory devices, and asthma alone accounts for a large amount of the population. And there are other diseases to take account for that would require normal spirometer, and that such things could be bronchitis or pneumonia. And as a result, we want to target two populations at first, one being general respiratory therapists, and the second being home users. And as Lucy alluded to, hopefully in the end, we will have a wireless feature, and that will have our product be a lot more affordable, especially for low-income families. And the way we plan to do this is first working locally, and especially with therapists at the UC Irvine Medical Center. And after a certain threshold of, for example, we reach 30 sales, we would like to follow up and validate with their opinions, how they're feeling. And from there, we would reiterate and work on the future generations of the device. And currently, we're working on sensor fabrication and new software. As you guys can imagine, the current game, it doesn't really allow for controlled breathing. So we're looking at golfing or fishing. And hopefully that's finished by April, May. We would work with the doctors and hopefully allow a first-person use, and hopefully integrate that feedback in June. And that's it. And if you guys have any questions, we'd be happy to answer them. Thank you.
So the component for the reusability is essentially the overall component of the device. The disposable criteria would be the sensor. So we want the sensor to last at least 1.5 hours of therapeutic exercising before you have to replace it, because we acknowledge that the sensor itself has a point where it needs to be replaced because it gets overstrained or overstretched after constant usage.
So for each physical therapy event, they basically use the new sensor?
Not each event, but over time. It's going to wear out eventually.
The sessions themselves or the therapy that they do usually last only a few minutes, so the 1.5 hour mark is just the fact that they use it multiple times because of how short the sessions themselves are.
You mentioned a new game that you're building for golfing or fishing. How do you incentivize people to breathe by a golf or a fishing game?
So for example, not necessarily that, but in the end of the day, we want to have the patients breathe in and exhale a certain amount. And as you saw from the current prototype, the rockets were falling at a very sporadic and very random movement, and we wouldn't want our patients hyperventilating. So for example, for a golf course, we could set a hole, a specific force away, and as you would inhale and then exhale to reach that distance. Or if it's the same thing with fishing, you would inhale to pull in the reel and exhale to throw out the reel. So it's more controlled and varied to the patient and user.
So you mentioned like different types of games. Would you consider having like
Yeah, eventually we'd like to basically have like an arcade style in which the patient can actually go in and choose, because again, the sessions are very short. So if you have different options to play different games per each session, it might actually keep up their motivation over the weeks of therapy that they're undergoing.
Would it be a bad thing if they like did the session more than once in a day? Like say the game was just really fun, they wanted to increase their high score or something?
Well, that's actually the whole point of the motivational aspect of it, is that they have to do it multiple times a day. That's why the sessions are so short. And we're trying to actually keep them to actually be engaged enough so that they actually want to come back and do it like they're supposed to be doing it. I can't hear him.
So it's from an Arduino and it's attached to Python, so the game's being run on Python with a interface basically that connects the two.
Oh, do you have your own screen thing or is it connected to your phone?
Right now, the current prototype is that it runs on our computers. Eventually, once we get the Bluetooth integration on it and we actually have like a more app sustainable thing, we want to transfer it onto an Android tablet.
Oh, wrong way? Gotcha. Hi everyone, I'm Ryan. This is Jen, Kos, Jiaheng, and Shin, and we are Team Slap Band. So currently, roughly 85 million people have high blood pressure, and only 54% of these people are aware they have this condition. High blood pressure significantly increases the risk for heart attack and stroke, and right now the current gold standard for monitoring blood pressure is with a blood pressure cuff, which can only take measurements at a single point in time. However, a person's blood pressure can change drastically throughout the day, so it's very easy for early signs of cardiovascular disease to go undetected. Our solution is to create a wearable blood pressure monitor in the form of a wristband that's capable of continuous monitoring, that is also comfortable and unobtrusive to the user's daily life.
Okay, like Ryan mentioned. Okay, like Ryan mentioned, we're basically building a wearable blood pressure monitor. So on the PPT, there is a configuration shows the sensor system that we use inside. When we put the capacitive sensor over the radial artery, the radial artery will apply pressure to the sensor, and the pressure will change the capacitance in the sensor. With the equipment in Michelle's lab, we can have a graph based on the changing capacitance, which will help us calculate the blood pressure later. And that's pressure band itself is supposed to apply a constant pressure to the capacitive sensor to make it work functional normally. Furthermore, to get rid of the influence of the applied pressure, we need force sensitive resistor to measure out the pressure that we applied by the pressure band. We also have the Bluetooth app help customer to connect their device like cell phone or PC to our device to get the real-time blood pressure data wirelessly. It's very convenient. So,
So for our current progress, we originally started out with the capacitive Wheatstone bridge, but the signals that we were getting were incredibly noisy. Since then, we've discovered an integrated circuit known as a capacitance to digital converter, and that handles all of the capacitance measurements for us.
So as the mechanical design part, the design idea comes from the smartwatch, such as Apple Watch. So our design direction is to make a convenient and practical product for our daily life. The bottom of the slide band is divided into important parts. Which are used for information transmission and charging device respectively. So another problem we face in mechanical design part. So it's we need a force to apply to the blood pressure sensor to make it get the signal from our skin. So we saw it finally through using FSR sensor to calculate the pressure range. So which is 40 kilobar to 57 kilobar. So finally, we came up with a way to give the pressure with the control by a specific spring. And as the material selection, we will also refer to the smartwatch, and we will choose a cheaper, more comfortable material for our further testing and modeling.
For now, we have made a user interface for Android, and the Bluetooth connection, we successfully received a signal from the Bluetooth connection.
And so we've identified a couple different design acceptance criteria. Essentially, we want the sensor to be sensitive enough to measure the changes in blood pressure, and for the band to be comfortable and fit everyone's wrist sizes. We also want it to sample continuously. So as long as it can measure changes of 0.5 picofarads and weigh the average weight of a wristwatch and fit the average woman and men's wrist size, it'll be acceptable. And if it can sample 200 samples per second.
Compared to our competitors, Slapband provides continuous measurement. It is easy to wear because of the small size, and all patients will be able to get this from their physicians in the future. The cost of it is relatively low because since the capacitive sensor costs for 10 cents to 25 cents, with a FSR wristband, capacitive measuring microchip and the Bluetooth chip, the total cost should be like $35, and we target selling price for $100.
Okay, for the failure model, it's like we have found the 4 principal problems we could have so far. Firstly, will cause inaccurate readings, and they are like capacitor sensor stop working, and for sensitive resistor stop working, and the band doesn't apply enough pressure to the sensor. So we can fix those problems by have the detective signal in the device. And the fourth one is that the Bluetooth connection failure, and we can fix that with like notification on the app. Okay.
So there's supposed to be some more info on this slide. Formatting got a little weird, but our market are physicians, specifically physicians who may have patients with hypertension or at risk for hypertension, or patients with cardiovascular disease. So we're targeting primary care physicians and cardiologists, and there are more than 200,000 of those in the US. So we have a huge market to go to. And the market for wearable medical devices, such as ours, is growing, and the US is the largest market for it. By 2020, the market's supposed to grow to $40.6 billion. So for our business model, we plan to get FDA approval and insurance codes to then sell our product to physicians. And physicians will then prescribe our watch to patients who will use it to monitor their blood pressure daily. The watch itself will have a band that's reusable, but the sensors are disposable, so they'll have to keep coming back to us for our sensors, and it will give us steady revenue.
So for our spring quarter goals, we're looking to do final validation on just the hardware components, and then we will validate the signals that we're collecting with the blood pressure monitor using a machine that was donated to the lab by Edwards. And then finally, once all the components are put together, we'll validate the final device as a whole. Thank you. Are there any questions? Yes. So the FSR is overlapped.
The FSR sensor just we get a range for the how much the pressure we need to supply. So we will do the device like this one. So it's very small. It will apply the pressure we used. Yeah.
So the user would basically have to tune it until your app says you have it on properly, and then it'll start recording?
Yes.
Yes.
So you say you're selling to physicians, but would this possibly be available like over the counter as well? Because I know plenty of people that just want to measure their blood pressure.
So we're going more for, I guess, clinical or FDA approval. The problem with commercialization is that a lot of physicians might not recommend a device that's just sold over the counter. It'd be kind of like akin to Fitbit or anything like from Apple. And so since they haven't really gone through as strict of FDA approval, physicians might be hesitant to actually recommend this device to their patients. Yes.
So since you intend for the device to be prescribed by physicians, have you identified an insurance code?
We've looked into insurance codes, but we haven't really identified anything specific just yet. So we're still kind of doing more research as far as, insurance. Yes.
So a lot of this relies on that spring, right?
Yes.
Have you looked into your material choices in terms of what types of springs would have the least amount of fatigue? Because it's going to be a continuous work device. That would
Right.
personally
We're trying to figure out right now, but we will test many materials and many materials of the spring. So we're gonna choose the final spring.
So you're going to do it.
Yeah.
Yes.
Why do you dispose your sensor? Why do you have to dispose of your sensor?
I'm sorry?
Why do you dispose your sensors? Or why are you throwing your sensors away as a custom environmental decision?
Because the sensors currently, they have a specific lifetime that isn't too long. So they're still being worked on and developed further. But at the moment, then they're good for a certain while, and then signals start to get a little off. So we just want to keep it accurate.
How do you prevent it seems like you would only get accurate readings if it's not only has the right amount of pressure, but it doesn't move on the wrist at all. How do you ensure that it doesn't slide on the wrist and give you a false reading?
Of course, on the mechanical design part, there will be a holder on the slab band. On the side, there is two holders. It won't move. So the blood pressure sensor won't move.
Any other question?